Hi, y'all. So today we're going to be going over the chapter 2 and 3 recitation group work. I accidentally mistakenly titled it 1 and 2, but it's more 2 and 3. So it's more about functional group and acid-base chemistry than much from chapter 1. So I start off with a lightning round where you brainstorm the following questions and then discuss your answers. And part of why I want you to do that is because probably your peers have found some good study techniques that maybe you haven't thought of, and so you can brainstorm together. And then also it helps you come up with a plan. So you're not like spending time being like, what do I need to do to study? Because you've already come up with a plan. So that's what that is for. And then activity 2, what have we learned in this class? Make major bullet points for topics you need to review. So I do this instead of a review sheet on purpose, and I do it in group work so you can come together as a group and do it. And you can, talk to one another on Canvas as well. But my big goal for this is for you to learn how to make your own exam reviews so that you can, one, take that skill with you to OChem 2, because Dr. Bearhay is also not going to make those for you, but also so that you can take it with you to other classes and into medical school, and so that you can really learn how to like organize your notes into something that's useful. And if you've gone chapter by chapter and made your little chapter study guides, then that will be even easier. So like if I was doing this for chapter 3, I'd be like, okay, well, chapter 3 is acid-base chemistry. And just off the top of my head, I think the big things we need to review is curved arrows. She said we're going to get the pKa chart, right? So you need to know how to use the pKa chart. You need to know how to predict which side of the reaction is favored or which side of the reaction are the products. And to do that, you need to be able to identify conjugate acid, and conjugate acid. Probably need to know definitions to be able to do that. These are the things I'm going to go through and like think about, like, oh, these are the things that are important for me to remember as I'm preparing for my exam on this chapter. And those are kind of the big things we covered, right? That's what I would go through. And then I would make sure I know how to do all these things, but this gives me an idea of what I need to review. Okay. I'm going to change pen so this isn't too dark. Activity 3, practicing functional groups. So draw an example of each type of functional group you need to know for this course. There's a slide listing this in the chapter. I'm not going to go through that since there's a slide listing it in the chapter, but ketones, aldehydes, and you can leave these as R groups if you want for your initial, kind of figuring things out. This is ketone, aldehyde, carboxylic acid, ester. Sometimes carboxylic acids, their shorthand notation looks like this. I think that's also beneficial to know, or COOR. You need to know alcohols. You need to know alkyl halides. You need to know halides are all of these. And you need to know amines. And you need to know if they're how to tell for this row, how they're primary, secondary, or tertiary. You need to know phenol, which if there's a benzene plus an alcohol, that's phenol. You need to know amides. I'm not going to go through all of them. This is just kind of give you an idea of what I would do. And you need to be able to know if they're primary, secondary, or tertiary. So you need to know them and have the names. And so this kind of sets you up for then this next question where you're going to have to see them in nature. So I wanted each one of your group members to do this, to find a functional group that's in nature, just because I think it's really interesting. So I'm going to go do some real quick. I'm going to search vanilla functional groups. And the molecule vanillin comes in, and it looks like this. So I'm going to say this is an aldehyde. This alcohol plus a benzene is a phenol. And this is an ester. Nope, this is an ether. Always get those mixed up. So that's I didn't have it drawn on there. So that's kind of what I wanted each one of you to do, that kind of searching and find something that relates to one of your interests that has these has these things in it. An interesting one that's in, I think, lavender. Oh no. Let's see what. Okay, well, this is DEET. This is not a natural product, but this is another cool one if you don't want to do one in nature. DEET, which keeps off mosquitoes. This has a benzene ring. This structure is actually an amide. So, this doesn't have 3 different functional groups though, but this amide has 2 R groups off of it, so you might not recognize it at first, but that's a good one. And then I'll do one more since that one didn't have 3 functional groups. Let's see, what's in lavender oil? So I'm gonna look up lavender oil structure. That's what I'm Googling. Lavender oil has linalool in it that looks like this. This doesn't have the number of functional groups I requested though. But it does have an alkene here and here and an alcohol. And is that alcohol primary, secondary, or tertiary? I spelled this so wrong. Alcohol. Put an extra O. It's 1, 2, 3, so that's tertiary. This carbon is attached to 1, 2, 3 other carbons, so that is tertiary. Okay, so that's just kind of what I basically wanted you to have the opportunity to look up how this applies to you in nature. Okay, so I'm not going to do this one too much in detail because in my own words is how I did my notes, but hopefully, or like when I presented it in class, but hopefully, the definitions of each of these. And very briefly, I'll say Bronsted acid makes protons, Lewis acid accepts electrons, and then the bases are kind of the opposite between them. And then an electrophile, I made that chart for you. An electrophile accepts electrons as well in the formation of making a bond with a nucleophile. And that can be a carbocation, but it doesn't have to be. Okay, so part 2, what pKa is of the labeled hydrogens? What is the pKa of the labeled hydrogens based on pKa's, which is the most basic and which is the most acidic? I wish I had my pKa chart here. I might have one somewhere. Hang on. Okay, sadly I don't have it. I posted a video in Canvas of me going through during office hours and actually using a virtual pKa table, but I don't have a virtual pKa table with me. So I will say, based on the pKa table, this pKa is about 25 off of a carbon-carbon triple bond. Off of a carbon-carbon single bond, it's 50, and off of a carbon-carbon double bond, it's 44 or 45. So I just remember 45, 50, 25 for those. If it's carbon with 3 other things bonded to it. This hydrogen has a pKa 50. It does not want to get got, does not want to be given up. This has 45, also does not really want to be given up. This, because of the S character, is 25, and it's more willing to be given up. Okay. Estimate the pKa of the bolded hydrogens. Based on the pKa, which is the most basic, which is the most acidic. So this is the most basic, and this is the most acidic because smaller pKa is more acidic. Okay, next question, same thing. We'd use the chart, but there are some things I kind of want to draw your attention to on this. Right here on this carbon-carbon triple bond, we're looking at this hydrogen. The pKa of that is 25, just like up here. Now on this, we're looking at a hydrogen bonded to an oxygen. And I think a lot of times students will look at that and think, it's like an alcohol, it's 16 to 18. But you really have to pay attention to the chemical environment. And actually in this case, it's less like an alcohol and more like a hydronium ion, right? Because it has a positive charge on the oxygen, and that pKa is closer to negative 1.7. So this is more similar to hydronium with an oxygen with 3 things and a positive charge than to a alcohol that has an oxygen that's only bonded to two things and not a positive charge at all. Because if it's positively charged, when you lose this proton, it's going to go to neutral and that's going to be happy. So, why wouldn't it want that? It would just be water that's incredibly stable. But if you lose this proton, you'll have what's called an alkoxide, so that's negative, so it wants to react. So this is much more willing to be given up than this. So this would be much more willing to be given up than a corresponding alcohol. So that's important. There's a similar one that often comes up with if you have a nitrogen, like this nitrogen right here, if it has a hydrogen directly bonded to the nitrogen and it's neutral, that's 38. But sometimes if it has a positive charge right there, that is actually, I think it's closer to 9. So you really want to pay attention if there's positive charge and make sure you're approximating the right functional group. This is a hydrogen that's right off of a double bond, so that's actually closer to 45. This is a carboxylic acid, so that's between 4 and 5. And then this is an amine, so that's 38. So now what are we doing? So I went through and found the acidic proton, or it told me which one was the acidic proton, and ranked or gave their numbers. And then I have to rank them most acidic to least acidic. So smallest number is most acidic. So the smallest number is, let's see, this one's negative 1.7 and this one's 25. So 2 is the most acidic, then 4, then 1, 5, and 3. So this is the most acidic, this is the next most acidic, then this, then this, and then this. So that's the least willing to give up, and this is the most willing to give up. Okay. Next question, what is the product of the following reaction based on curved arrows? So label what is the acid, what's the base, what's the nucleophile, and what's the electrophile. So based on curved arrows, this lone pair right here, I'm actually going to use colored markers for this. I think it would be easier for you to follow the flow of electrons if we use colored markers. So this lone pair right here is making a bond to this hydrogen. So if we just stopped right there at that, you'd have this oxygen bonded to this hydrogen, and then a new bond is starting to form between that hydrogen and this oxygen that has a CH3 and 2 other lone pairs. So this lone pair is starting to become this bond. But you can't have that many bonds to hydrogen, so then this breaks so that the hydrogen can be happy. So the completion of this first set of arrows, I'm going to stop right here, one step at a time, leaves this negatively charged, and you have a hydrogen that's bonded to an OCH3. And we'll say that I'll use my colored markers again. I use a different color. So say this bond is teal, that pair of electrons is teal, so randomly I just assigned that one to be teal. So this bond, the 2 electrons that make up this bond, broke and went to this oxygen, and the 2 electrons that were the excess electrons here made a bond to hydrogen. So that's kind of where those electrons came from. But there is one more arrow. Oh, I drew this backwards. It should be, it doesn't really matter. I could just draw it upside down, but there is one more arrow set of arrows. This actually comes here, and this breaks. So if this set formed a new bond right here, and then I'll do yellow, and then this bond comes and goes right at the top. So our final, that's kind of hard to see. I'll do green. This comes and goes right at the top. So the final structure for this one would actually be a lone pair here that's from the green, a double bond here, and an oxygen here. So the double bond here came from, originally, it was this bond between this hydrogen, and then this lone pair used to be that green right there, and then these other two don't get messed with. I'm going to cover that up. So I stopped before I did the whole chain because that's kind of a long chain. So I wanted you to see like the lone pair stop on the oxygen. But you can do the whole reaction right at once where you see this oxygen bonds to this hydrogen. And then this goes here and that breaks. And so we end up with this. But for me, it's easier to go step by step. Okay, so these are the products of the reaction. It's this and this. And I'm supposed to label. I found what the product of the reaction is. Acid and base. So the acid is going to be the thing that gives up the proton. So in this case, this would be the acid because it gives up a proton. And it also accepts the electrons from this. This hydrogen accepts the electrons from this bond. So that's the acid. And this is the base. And then the conjugate acid is what accepts the proton, and the conjugate base is what gave up the proton. So then what is the nucleophile and what's the electrophile? The nucleophile is the thing that attacks. And this electrophile is the thing that's being attacked. So nucleophile, electrophile. And then we can even go a step further and predict the products of the reaction. So the pKa of phenol is actually 9 to 10. That is on your chart. It's written as C6H5OH. Shorthand for benzene is C6H6. And if it's substituted, it's C6H5, and then whatever your substitution is. So the pKa of that is actually 9 to 10, and the pKa of this acid that's an alcohol, so 16 to 18. So this arrow is correct because this side of the reaction is favored. Okay, now for the following, we'll do the same thing. Label the acid base, the conjugate acid, conjugate base, give the pKa's, and draw the curved arrows. I'm going to start with the curved arrows because that makes the most sense to me. So the chlorine will attack and take one of these hydrogens, doesn't matter which, and then this bond will break and form a lone pair here. So this bond becomes, there's already a lone pair that's not drawn in on this side. This bond, because the new lone pair, doesn't matter which, they're essentially the same. And then we'll say this lone pair becomes this bond right here, but there's still a whole lone pair all around this as well. So those are those implied electrons. So that's where those bonds were made and broken. So this bond became this lone pair, and this lone pair became this bond. And so the arrows show that. And then let's label all the things. So the acid here gives up the proton. So this much must be the base. So this is the conjugate base, and this is the conjugate acid. Label the conjugate acid, conjugate base. Give the pKa for the acid and the conjugate acid. So this is negative 1.7. I would have gotten that from my chart, or you can work towards memorizing it. And this, I don't have this memorized, and you don't need to have it memorized either. What is the pKa of HCl? I'm looking it up. I don't have my chart handy. You should have your chart on your exam, so you need to be able to recognize that. This is negative 8. So which side of the reaction is favored? Well, there's that whole high to low. It will go low to high. It won't fly. Or I just remember the weaker acid is favored, and that's the smaller pKa. Whichever one of these makes the most sense to you, but this is negative 7 and this is negative 8. So this is a smaller pKa. Oh, wait, no, this is the smaller pKa. This is more negative. But the negative 1.7 is smaller than negative 8. So this is the weaker acid. So this side is favored. So the arrows would probably be more like this, actually. Oh, wait, should be on the bottom side. And that's a good example of a leveling effect. So if you had hydrogen chloride and you dissolved it in water, it literally will not be able to get more acidic as a pKa than negative 1.7 because it'll just react with the water and hydronium will be the favored side. There might be a little bit of that HCl left, but it's not going to be a lot of the HCl. Okay. And we already did the curved arrows. Okay, so next, we're doing the curved arrows to show how the major products came to be. So actually I should have done the curved arrows on this side. I didn't even follow my own instructions. That's why they came last. That makes sense. So if the reaction was going this way, the curved arrows would be the water takes this proton and this bond breaks, and then you end up with H3O plus and Cl minus. So if we were going the opposite way, this lone pair became this bond, or this lone pair, whichever, and this bond became that lone pair. Okay, that makes so much more sense why I did it last. I was like, why would I do that? Okay, so we'll do this one in the right order. Label acid and base. So acid is the thing that's going to give up the proton. If you're not sure between which one of these is the acid or base, this pKa is 25 and this is 38. So this is more acidic and this is more basic. Also, this extra lone pair is kind of a hint that it's willing to give up when this one might not, or that it's going to be an electron donor because this one can't be an electron donor. So this is the conjugate acid and this is the conjugate base. So let's see, pKa of this is 25. pKa of this is 9. So this is more acidic. This is the weaker acid. Okay. So this side of the reaction is favored. So the proper arrows would be like this with just a little bit going back this way. And if you want to think of the high to low, it won't go. So 25 to 9, high to low, it's not going to go that way. Larger number to smaller number. But low to high, smaller number to larger number, it will go because it wants that weaker acid. And now we're going to draw the curved arrows to show how the major products came to be. So I'll say this conjugate base would come and attack this hydrogen. And then this bond would break and go back to itself. And that's how you end up with this nitrogen. Basically, this bond became this lone pair. And this became the bond between the carbon and the hydrogen. Okay. And part 6, for the following compounds, predict which one will be the strongest and justify your choice. Don't just use pKa tables, although you can. Think about charges, resonance, or induction to justify your choices. So we already talked about the fact that phenol has a different acidity, but if you're just looking at this functional group, both of these just look like regular old alcohols, so you'd think they'd be in the 16 to 18 range. This would be the most acidic hydrogen present, so this would be a pKa of 25. And if you look here, there's not a hydrogen there, right? Because there's 1, 2, 3, 4 bonds to carbon already, so there's not a hydrogen there. And the hydrogens at this point of the molecule have a pKa of like 50. So it doesn't make sense to pull those off if you could pull a more acidic one off. Versus H2. I'm pretty sure H2 has a pKa of like 35. And then this is protonated. So the protonated version of this is going to act most similarly to NH4 plus, not NH3. So the pKa of this is around 9. And the pKa of NH3 is around 38. So again, I'm looking not for this exact molecule, but I'm looking for something that approximates the behavior of this molecule. So I don't need to find this exact thing on the pKa chart. I'm looking for NH4 plus. I don't need to find NH with a methyl and this propyl over here. I just need NH3 basically to approximate it. And then HCl, I believe we just found was -8. And H2SO4, I'll check my pKa chart because I don't have that one memorized. It's -5.2. So you can answer almost all of these based on just pKa's. For you can predict that the Strongest acid is going to be the one with the lower pKa, or the smaller pKa. So, this one here, and this one here. If I didn't have a pKa table, I would be able to think about the electronegativity difference here, that this HCl is already really electronegative, so this hydrogen is positive, so really more willing to be given up than this H2SO4. It's less positive. H2SO4 looks like this, right, with all the lone pairs around it. So this OH bond is going to be less polar than this HCl bond. So that's something I could think about to reason my way through this one. On this one, all I would have to think about is like, this is positive. So if this positive species lost a proton, then it would become neutral. And you would always rather, like nitrogen is pretty electronegative, it would always rather be neutral than positive. So it is very willing to give up that hydrogen. So I would be able to guess at this even without looking at the pKa table. This one's a little bit trickier, I think, because this is sp hybridized and this is just S overlap. You could think about that, but I don't know. I would just use the pKa table on this one. This one's kind of hard to reason through. Now this one, you can assume that all alcohols are 16 to 18, but actually we know that phenol, which is its own functional group that we learned, has a pKa of 9 to 10. So if you know that, then you know this is the answer. Or you can use what's known as the resonance effect, right? So if we look at the conjugate bases of both of these species, sorry, ignore that scribble. That was a mistake. They both are negative, but this negative charge can be spread around the molecule, right? So it can at least go here. And it can actually keep going around the ring where there's multiple resonance structures that spread that negative charge out all over this molecule. So instead of one molecule or one atom feeling, this bond goes here. Instead of one atom feeling the full effect of that negative charge, it's spread between the oxygen, this carbon, and this carbon, instead of being concentrated in one area. And so that makes this conjugate base more stable, so less reactive. So it's a weaker conjugate base because it's more stable. So it's less likely to react. So that makes it a stronger acid. So you can think of the acid in terms of how good is the conjugate base at stabilizing what's left behind. The more stable the conjugate base, the more acidic the conjugate acid. And that's, sometimes we also think of it as like weaker conjugate base, or the more acidic the acid that goes with it. Sometimes we think about weaker base, stronger acid. More stable and weaker are the same because those are referring to its ability to react. And the more stable something is, the less reactive it is, so the weaker it is. So if you think of like someone's emotions, and if they're really reactive and they're pretty unstable, they are going to be coming at you with a strong push of emotion. But if they're really stable, their emotions are going to be weaker and they won't be as reactive. So more stable is weaker and less reactive, and then more acidic is more reactive and less stable. So always think about that in terms of the conjugate base. And then we did talk about in office hours as well, if you just want to check that out, how you can justify things like if you have the same functional group like this, how you can tell which one of these two is more acidic using the inductive effect. And I'm going to leave that as a spoiler, so you have to go look it up. Okay, I hope this was helpful to you. Good luck studying.